Welcome to chapter 10. So, we will again still stick with generalizations of RMA. So, any realistic, practical, real time operating system will actually support a limited number of priority levels. So, the reasons we have seen in the previous lectures. So, one is that to create a data structure, you could of course use a heap and so on. But they are again order log n time data structures. If let's say you want to do something which is more efficient, then what you would like to do is have one of those order one kind of structures which deal with a fixed number of priority levels, right? So in a sense, whatever priority we get, we need to map it to one of these levels. So this will reduce the scheduling overhead. And furthermore, your response time and throughput will suffer a little bit because the scheduling will become slightly suboptimal, but that's okay. In For a practical reason, for a practical consideration, this has to be done. So it should be understood that any practical or realistic operating system needs to support a limited number of priorities. It needs to support a few priorities, not many. When the number of tasks is more than the number of available priority values, then of course there is a need to map. And again, for the same priority, we may have multiple tasks. We may follow round robin scheduling between tasks of the same priority because there is no choice, or we can also look at FIFO and EDF for the same priority, right? In the sense that the first level scheduler RMS, for instance, can map a task to a priority level, but then if there are multiple tasks at the same priority level, something needs to be done. So let me just clear the clutter on this slide. It will help us look at things better. So naturally, this any kind of deviation from the ideal will reduce the schedulability of the system. But the question is that how do we create a practical system that is assign priorities to minimize the impact? So well, one approach is that we can choose priorities on a grid in the sense that we can take a 2D axis of tasks and priorities and somehow choose them where tasks are, let's say, in ascending or descending order of precedence. So then there are different schemes of doing it in the sense that we can have uniform schemes or geometric or logarithmic schemes where if it's a curve like this, then many tasks with low priorities. So let's assume that lower is this number, higher is the priority. So many ones with low priorities will have more or less the same priority level, whereas the difference will be substantial for high priority tasks. So basically, an inverse of this curve might be something like this. So clearly the idea is that many tasks at the end, if they're a very low priority, you would want them to be roughly at the same level because it doesn't matter, and you would focus on a finer granularity of tasks over here. So, how exactly you do it, that is very much dependent upon the application at hand, in the sense how much of differentiation and queuing you want. In a certain sense, if it is uniform, then across the priority levels, you'll roughly have the same number of tasks. If it is not uniform, then let's say if this is a high priority level and this is a low, you'll have a few tasks over here and you'll have many tasks over here. So, particularly for low priority tasks, they will get a raw deal because even between them, there will be a need to run a scheduler, and so that will further slow them down. But the advantage is that some tasks at the top will get benefited. So, the uniform scheme, the idea is that if there are n tasks, capital N, and small n priority levels, then all that we do, sorry, a small correction here. So, this should be floor of n by n, right? Tasks divided by levels, not this. So the key point is that floor of capital N by small n tasks should be assigned to each level. Roughly you want to homogenize, and of course a few that are left could be distributed particularly among the lower priority levels, right? So Essentially, if I were to look at the priority levels, at the top it will be roughly the same. Any extra, it goes in over here. So an example over here, let's say we have 6 tasks and 4 priority levels. So then you can see the 4 priority levels over here. So the way the assignment we can do is that the highest priority level could go to T1, task T1. The second to task T2, the third priority level could go to T3, T4, and the last one to T5, T6. So you clearly see a degree of non-uniformity towards the end. So here again, the idea is that what we can do is that we can, look at the density. I'm looking at a general example. I'm not looking at this example in particular. So let us say that we create ranges from 0 to A1 and then A1 to A2, A2 to A3 and so on. And then we look at the period of each task. So basically we just put them over here. And the ranges need not have the same size. If it's non-uniform, the ranges at the end could be larger and the ranges at the beginning could be smaller. In the sense this could be small ranges and these could be, for example, much larger ranges. So then basically you would look up the period of a task and this will basically tell you in which priority box it falls. And so let's say the period is 10, it will fall here. If it is 20, it will fall here. 40, 60, it will fall here. So it all depends on how we draw these lines to tell us where the priorities lie. Then is the arithmetic scheme where of course we assign the priorities in a different form. Basically what we do is we look at smaller tasks having the shortest periods. So they are assigned to the highest priority level. Then we take the next 2 hour tasks assigned to the next highest, then 3 hour and so on. So if you have n priority levels, then, uh, you know, and let's assume that we have an exact equality. So then this will become this basically summation of 1 to n, right? So this, across all I will just sum it up from I equal to 1 to I equal to n. So this is nothing but r times n plus 1 by 2. Okay. So this will basically be the equation. Where if you would look at the priority grid, we will have this will be r, this will be 2r, this will be 3r, so on and so forth. All right. So we could alternatively draw a curve in the sense these could be, let's say, priority 1, where lower. I mean, this is a priority number. It's not really a priority because in this case, lower the number, higher the priority. This could be priority 2, this could be priority 3, so on and so forth. We can either draw a step function, or what we can do is we can just take a line and we can just split it, where the length of one split is r, other is 2r, other is 3r, such that this equation is approximately correct. So this would be another way of dividing tasks into bins, where clearly the high priority tasks are in the highest bin. So this is an example of a geometric scheme where we do again the same, but it is just that in this case we divide it differently, r square, r cube and so on till r to the power n. So this would again more or less achieve the same thing in the sense that these will be, the priority number 1, 2, 3, 4 and so on. In this case again lower the number, higher the priority. So this has a very simple solution, which is basically r raised to the power n plus 1 minus 1 divided by r minus 1, right? And so this should be approximately equal to n, and on the basis of this, the value of r can be decided. So here, depending of course upon the value of r, the priorities are way more skewed. So basically the arithmetic scheme in a certain sense was slightly fairer than this, where polynomially the size of each bin increases. So again, this has to do with how much we would like to prioritize a few high priority tasks in comparison to the rest. So experiments show that such a logarithmic grid, so which is basically r square and so on, as we have just seen over here, works the best in the sense shorter period tasks are allotted as many distinct priorities as possible to differentiate between them, and longer period tasks are kind of all binned into the same bin. So here, of course, we are assuming that the maximum period divided by the minimum period to the power 1 by n is equal to r. So just go back to the end here. So basically what we are, one of the assumptions is that if this is the ratio of the periods, then it nicely captures this as one of the values of r. So if we take a look at the last term and look at if we set the last term equal to p max by p min, it kind of tells you that in if we were to draw a logarithmic grid like this, then pretty much I start with a p max and a p min, and every time I multiply by r. So after n steps, I'll reach p max, on a log scale. So this is basically all that it is trying to say. That if I increase the priority n times, or if let's say I have n prior number of priorities, and if r is equal to p max by p min to the power 1 by n prior, all that it says is that on a log scale, with n such multiplications, I will reach from p min, I will reach p max. So if I were to draw the grids, so more or less this is the way it would look. You will have smaller grids. They will keep on increasing, as I said, in the ratio r square, r cube, and so on. So of course, what could happen is that if p max is 100,000 and p min is 1, and there are 32 priority levels, then r will come to 1.43. So the grid lines will actually initially be close, and then gradually the distance between them will increase. So in the first few grid lines, actually, you may not be able to fit a lot of tasks, and even at the beginning, because some of these grid lines will be so thinly spaced that some of them will also remain empty. You will not be able to fit tasks within them. But that's all right. The key point is that we are doing a much better differentiation with tasks with smaller periods, and gradually the between like an expanding barcode kind of thing, gradually towards the end you will essentially bucket all the low priority tasks. So here we are kind of fine tuning the scheduling algorithm for all the high priority tasks by basically designing the binning in such a way that we are looking at them in kind of great detail and optimizing our algorithm for them. And pretty much we are seeing all low priority tasks regardless of their precise periods. They are treated the same way. So next we will look at another facet, another practical aspect. So having a limited number of priorities is one aspect. Another practical aspect is task jitter, where there could be some variation in the arrival or the completion time of a task. So recall that we have discussed variation in the completion time of a task in earlier lectures as well, where our idea was that we take the remaining amount and we either create an aperiodic task out of it, or we look for opportunities where there is slack. So if you want to minimize jitter as much as possible, for example, a real-time controller can get quite unstable in the presence of jitter. We need to have elaborate mechanisms for managing jitter, because we cannot assume that there will be no jitter. That is going to be impractical. So as I said, we will have arrival time jitter, right? So we need to create a range. One simple option is to essentially assume the worst case. The other is we'll have completion time jitter, right? So again, there will be a range. So of course, it is always the best to reduce it and ensure that the jitter is zero, but that may not be possible. Hence, it is important to reduce it at the source level. If that cannot be done, then our scheduling has to take that into account. So the task completion jitter can arise because of many reasons. One is that it arrived late. The other is high priority tasks arrive late. It is also possible that when I was doing the analysis, I considered a certain code path, and instead of this code path, some other code path actually executed. And this is not something that I had planned for or I had simulated. So, in that case, that will take a different amount of time, a different duration. Then, of course, we could have caches, issues with caches, issues with the bus, because the more elaborate computer architecture structures we have, the more jitter they can suffer from, the more execution time variability they can suffer from. And then, of course, we will have interrupt disabling, interrupt issues. So it is a much better idea to disable interrupts. Otherwise, interrupts can come in the middle, that can cause jitter. And also, if other processes are accessing the bus, that can cause jitter. So we may want to take up exclusive control of the bus if you want to reduce all of that. But mind you, such actions may actually introduce jitter into other tasks because some interrupts cannot be disabled forever. They will again show up either in a later instantiation of the same task or in another task where it will cause jitter. Furthermore, we could have jitter with the response time in the sense there could be critical sections, again, hard to predict. And, moreover, it's quite hard to predict other facets of task execution and arrival, which is well beyond our control. So assuming a worst case or a statistical worst case or a mean plus 3 sigma kind of thing, and then optimizing for that is a reasonable solution in such a setting. So usually response time jitter of the form that we have seen in the previous slide, that is typically the most prominent, where of course the response time shows a degree of variability. Sometimes it's easy to control, but sometimes it is much better to manage it as opposed to trying to control it. Manage it means manage things around it. So the task completion jitter, as you can see, for example, could happen because of irregularity in either the scheduling, in our estimates, in IO devices, interrupts, anything, right? It could happen. This is indeed a possibility that, for example, if these are the ideal timelines, if this is what is ideal, then indeed it is possible that something could be arriving here, coming here, here. As you can see, there is a jitter. Furthermore, preemption could be a prominent cause of jitter because preemption brings in the OS into play. And given the fact that the OS has come into play, its execution need not be deterministic all the time because many a time when the OS comes into play, right? So I have a task, right? I was executing it, the OS comes in here. The OS may have some of its own work, okay? So because basically the OS will have some of its own work, some of its own scheduling work. In that case, the OS will do its own work, which again may have a non-deterministic completion time before it schedules the next task. So we have to keep this in mind. So to deal with task jitter, approach one is it is applicable to situations where we have a set of tasks which is highly schedulable, low utilization. One or two tasks have a slightly high jitter requirements. If one or two tasks have a slightly high jitter requirement, we can assign these tasks high priorities, such that what will happen is that given we have sufficient tasks, sufficient slack, because our utilization is low and our task set is highly schedulable, if some tasks just take up some more time, nothing catastrophic will happen. Our system will still remain schedulable, but it will be easier to manage jitter in the sense that our system will have a sufficient degree of flexibility to accommodate for that additional time, the jitter time. Approach 2, it is for a task set which is barely schedulable, which means its utilization is high. So every task with a jitter constraint is split into two or more subtasks. So mind you, we have done the same previously under different contexts, right? For different reasons. So we have done it mainly to increase schedulability, but in this case, it improves schedulability in a different manner. So we split it into two tasks, one that computes the output and the other that passes the output on to other modules. So it is like a splitting of tasks based on their personality. So what we can do is the one that computes the output could have a lower priority, and the last task's priority, right? Which is to quickly, if you have something to quickly pass on the results such that others can start quickly, right? So because if you see, well, in principle you may argue that both are on the critical path, so we can increase the priority of this and stop this. But the point is, in the second case, unnecessarily the value even the computed would be hanging on. So this of course is a long debate on whether I should increase the priority of both or just one. But both may be a tough call because the task set is barely schedulable, so we can keep one low and one high. So in that case, what will happen is keeping the same period. If the priority of passing the data is high, then at least once it is computed, the rest of the tasks will quickly get the result. Now the point is that if it's a compute only task, which typically may not have system calls and so on, like which is not prone to preemption and self suspension, the jitter is expected to be lower in a compute only task as opposed to a non compute task. So it's a better idea to place a bet on the compute task, have it run at a low priority, and the other part of the task, which is let's say T1 and T2, right? So where a master task is split into these two, take the part that passes values and run that at a higher priority or a much higher priority. So the approach to the idea is that the initial subtasks will have soft deadlines scheduled at lower priorities. So then if the last subtask is delayed beyond the deadline of the initial tasks, in the sense that just in case if the last subtask, which in our case is passing the values, if let's say, so the way that I would compute the deadline in this case is I would take the worst case response time and subtract the execution time of it. So this would be the additional slack that it would have. So then let's say that if we perceive a delay or we perceive a jitter, so at that point of time, dynamically we assign it a high priority. So this means that our system should support the idea of dynamic priority assignment, where essentially you take a task. So there are two things. You split a set of tasks. Some get low, some get high. And even for the high priority tasks, initially it could be running at a low priority. But the moment it starts missing its deadline, we dynamically jack up its priority. So let's say starts missing its deadline, we just jack up its priority such that it becomes a high priority task. So the bonus problem is to devise an experiment to accurately measure the completion time jitter of a task. So of course this can be done. We need OS level hooks to do that, but doable again. So this brings us to an end of this lecture, which is lecture 10. So then there are a few more slides. They are mainly about quizzes and bonus problems. So we finished a very important discussion on some extensions of RMA. So the key point is that the RMS scheduling algorithm uh, is optimal, but of course it does not take into account some important things. One is discrete priority levels, something that we talked about now. And the other is what we also talked about, which is task jitter. So this is also not really taken into account, but it should be taken into account in the sense because in a real world, you are expected to face these problems and engineering solutions have to be designed beyond the maths that was shown to actually take these realistic problems into account, because the basic algorithm is simple, but then when you add layers and layers and layers around it, then it becomes a practical algorithm, because in the real world, right, in the real setting, you are expected to face all of these problems.